The ground you are standing on right now is actually accelerating. Surprised? You don't feel it directly, but you experience it all the time without realizing. Let's test this with a simple example. Imagine dropping a ball the way Newton once saw an apple fall. Newton explained this as gravity pulling the ball down through a force of attraction. But Einstein disagreed. He said gravity is not a force at all. And if Newton was right, he should have shown how this mysterious force is created, which he never could. Now let's try a bottle experiment. Suppose I make small holes on all four sides of a water bottle. If I hold it up, water flows out. But the moment I drop the bottle, something strange happens. The water stops flowing. Why? Because during free fall, both the bottle and the water inside are weightless. No force is acting, so the water flow halts instantly. This perfectly matches Einstein's view. The bottle is in inertia, not feeling any real force. That's why Einstein said the ball isn't falling. The ground is rising to meet it, as if the Earth itself is accelerating upward. Here's the mind-bending part. This acceleration happens in every direction toward Earth's center. That's why whether you're at the North Pole or South Pole, the ground still meets the ball. Sounds odd or even absurd at first, but this is Einstein's theory, experimentally confirmed many times. The reason it feels so strange is that we grew up only with Newton's explanation. Common sense often tricks us into resisting new ideas. Yet Newton's laws failed to explain some things like Mercury's orbit, where Einstein's model worked perfectly. So how does Einstein describe this accelerating ground? Earth's mass bends space-time around it. Only mass and energy can curve space-time, and because of E equals mc squared, they are interchangeable. In this curved space-time, objects naturally move along bent paths. Their direction changes, not because of a pulling force, but because they are following space-time shape. Newton thought a gravitational force acts. Einstein said, no, there's only curved geometry. Picture a spaceship outside Earth's gravity. Two cases. If it floats freely with no acceleration, then in space-time it is actually in free fall, moving along a straight path called a world line. This is inertia. In space-time, it falls forward at the speed of light, though not in space but in time. That's why in the absence of acceleration, it moves entirely through the time dimension. If the spaceship accelerates, part of its motion shifts from the time dimension into the space dimension. Time slows down for it. This is time dilation. Einstein explained that all objects always move through space-time at the speed of light. That motion gets shared between space and time. And for him, acceleration is nothing but deviation from free fall. Now think about this. Inside a spacecraft, as long as you're weightless, you feel nothing. But once the ship accelerates, the floor presses against your feet, you feel weight. Einstein's equivalence principle shows this is exactly what gravity feels like on Earth. If the ship accelerates at 9.8 meters per second squared, you'd feel the same weight as on Earth, meaning the gravity we sense here is not a real pulling force. It's simply the ground accelerating into us. What then is real gravity? For Einstein, real gravity is just the curvature of space-time. On a curved surface, parallel lines eventually meet. So imagine two objects falling from opposite sides of the Earth. They follow curved paths that converge toward the center, not because Earth pulls them, but because space-time itself bends. The Earth's surface resists collapsing into its own center thanks to electromagnetic forces between atoms, while space-time pushes everything inward. In black holes, mass is so extreme that nothing can resist. The star collapses completely into space-time itself. So when you drop a ball from 5, 10, or 15 feet, what happens? Locally, their paths are almost parallel, so real curvature hardly shows. That's why Newton's simple force law works so well at short distances. But if you release objects from millions of miles away, their paths diverge due to curvature. That is when Einstein's real gravity becomes clear. So here's the distinction. Curvature equals real gravity in Einstein's model. Apparent gravitational pull equals the illusion we feel on Earth because the ground accelerates into us. Newton treated these as the same. Einstein separated them. At small scales, Newton's model is a good approximation. At large scales, only Einstein's curvature explains things precisely. Newton taught us to see gravity as a force pulling apples down. Einstein revealed it as bent spacetime making the ground push up. One saw the universe as clockwork, the other as a flexible fabric. So who was greater? Newton gave us the rules to play the game. Einstein handed us the hidden codes of the game. And the next breakthrough? That could be yours.